This week we study Chapter 11, Rotating Frame. This rotating frame is involved with the inertial force. Inertial force is the frame-dependent force. That means the inertial force disappears when we consider a problem, mechanical problem in a reference frame. That means the effect of a non-inertial frame. The force that appears in a non-inertial frame is called the fictitious force or non-inertial force. As two examples, we consider the first example is the rotating frame-dependent force that consists of centrifugal force and the Coriolis force. First, let us consider a uniform circular problem, uniform circular motion. Something is rotating with a constant angular velocity. In order to keep the particle moving along a uniform circular motion, we need a centripetal force that is toward the center of the circle. That is a real force. Instead, we consider a frame that is rotating. In that frame, a straight line, that means a particle under no force, a free particle is moving in a straight line. In that case, according to the radial components, because the frame is rotating, the particle's distance from the center increases. Therefore, in the frame where the axis is rotating, it feels like the particle is experiencing acceleration, that is a radial direction, that is opposite to the center. So that force is called the centrifugal force. So centrifugal force is not a force, but it looks like a force, but it depends only on the frame of reference. Coriolis force is another example. If something is going forward in a straight line without force, so free particles motion, but when the frame of reference is rotating, in that frame, this straight line looks like a curved line. The opposite to is a rotation. So this curved line shows that in the non-inertial reference frame that is rotating, just straight line is treated as a curved line. That fictitious force is called Coriolis force. First, let us consider the angular velocity and angular acceleration about a fixed axis of rotation. Omega, the angular velocity, is defined by the time rate of this angle, and omega vector is parallel to the axis of rotation, and the magnitude of the angular velocity is the time rate of this angle. This omega is the time derivative of the angle, and we usually write it as a theta dot. Angular acceleration alpha is the time rate of changing the angular velocity and parallel to the direction of axis of rotation. Then this is second order time derivative of the angle, so we write n hat times double time derivative of angle. Consider a particle described in an inertial reference frame this is position. If I take the time derivative, then we obtain the velocity. That is a normal way of finding the time derivative of a vector in an inertial reference frame. However, if the frame of reference is rotating, if the particle is rotating about this axis, as well as the time derivative of this particle relative to the head of this arrow, that is x dot. This, because of the axis is rotating, there is an additional velocity appears due to the motion of this vector, the fixed radius, but some depending on angle. That we usually write it as omega cos x. Let's see why this appears to be in this form. Consider a finite rotation of a vector about the z-axis. This vector is on the xy plane, so this vector and transformed vector, due to the rotation, all of them are on the xy plane, that is perpendicular to the axis of rotation. If we consider the transformation rule for this vector, each component transforms like this. So x prime has the component cosine x1 minus sine x2. x2 prime is obtained as x1 sine theta plus x2 cosine theta. The difference between these two vectors is the delta x, that is the resultant change due to the rotation. And the angle of rotation theta is treated to be finite. So for any value, we have this contribution. And if we subtract the original value, that means this x1, x2 equals identity times x1, x2. Therefore, we subtract the identity matrix from the rotation matrix. So if we pull out the diagonal component, that is the identity matrix, and off diagonal component, that is the anti-symmetric matrix, minus 1, 1. So over factor will be cosine theta and sine theta for the diagonal component and anti-symmetric component. If I pull out the ij element of this matrix, the first one, identity matrix, ij element of the identity matrix is the chronic delta, and here 1, 2, and 2, 1 off diagonal components only survive. Wait a second. So 1, 2 element is minus 1, 2, 1 element is plus 1. Therefore, it is the same as minus epsilon ij. Epsilon ij is the two-dimensional rank 2 Lebesgue tensor. That means epsilon 1, 2 is 1, 1, 2, 1 equals minus 1, 1, 1, 2, 2. Both of them are vanishing. So this is minus epsilon ij. If I multiply this vector in here, I just connect the dummy index j. So multiplication gives, this is xi, multiplication this one gives epsilon ji xj. if I exchange the I and j, this negative sign disappears because of the permutation. Epsilon jij can be written in the form epsilon jij, and this index, for example, 1, 2 equals 1, and the 3, 1, 2 equals also 1. So I can rewrite this one in terms of epsilon 3 something. So 3 ji keeping the same value, I extend it in this form. And now I is shifted to the left hand side, so I 3j xj. That means this is the ith component of the cross product between cross product of E3 hat and X, right? As a result, this one is replaced with the ith component, and summing over the all ith components, we reconstruct the finite change of the vector due to the rotation by a finite angle theta about the z-axis in such a way. We are interested in extending this expression to a most general case. Consider we have remember that we have considered the axis of rotation that is perpendicular to the plane on which x and the transformed matrix, transformed vector x prime are both placed. So we copy this previous result and substitute the value x perp in here. X perp means this is axis of rotation, and we will extend this one, generalize it to arbitrary unit matrix, and then we have x. We were considering the case on in which x is perpendicular to the axis of rotation, but it may have a perpendicular component and a parallel component as well. So x can be decomposed into the perpendicular component perpendicular to the axis of rotation and parallel component that is parallel to the axis of rotation. The parallel component can be pulled out by taking the scalar product with the x and axis of rotation unit vector, and this is the magnitude, and direction will be the direction is this. And perpendicular component can be obtained by subtracting x by x parallel. Therefore, the perpendicular component will be obtained this way. Substituting this parallel component, we obtain x minus n hat dot x. Now, we substitute this perpendicular component in here. So, perpendicular component will be substituted in here to obtain this vector. Now, we have flipped the sign, therefore, okay, no, this just copied in here. Perpendicular component. And sine theta n hat cross x. Actually, it used to be perpendicular. However, even though I include this parallel component, because n hat cross x parallel is 0, because x parallel is parallel to n hat, and n hat cross n hat equals 0. Right. Now, n hat cross x appears, and this component also appears. But we can make use of the back cap rule. For example, a cross b cross c equals back cap b ac BAC minus C A dot B. So by making use of back cap rule, this is a B AC, they are the same. B AC, they are the same. Therefore, this one A and C are n hat, B is X. Therefore, we can replace this one with n cross X cross n. But if I exchange these two, we have n cross X, and this cosine theta minus 1 becomes 1 minus cosine theta. Right? This is the complete expression for the finite rotation about the axis n hat. So the result shows that we have axis of rotation n hat, arbitrary vector that does not have to be some phi. It is not perpendicular, and we have a plane made of n hat and x. We have a cross product of n hat and x to find the tangential direction. We increases the angle theta in this way, so this vector is along the tangential direction. And then we have another vector that is perpendicular to both this and this axis. So just like opposite direction of x-axis is needed, so we take the cross product n cross x to find the perpendicular component. So n hat, n cross x, and n cross x, these three vectors are perpendicular to each other, and they are cyclic. N hat plus times x, n hat times x. The final result is called the Rodriguez formula of a finite rotation. Okay. If I take the derivative, we have the first order derivative to be this one becomes cosine, this one becomes a sine. Second order derivative will be minus sine and cosine. And if we substitute theta equals 0, and at that instance this one becomes 1, and this one disappears, and this one survives, and this one disappears. So at theta equals 0, the rotation effect has the first order derivative n cross x, and this one involves the second order derivative. In the beginning, we stated that if the axis, if the reference frame is rotating, the total time derivative of the particle observed outside of the rotating frame is that this is due to the coordinate change measured from the rotating frame, and this is the amount of change, the amount of velocity generated by rotation. So this theta is the amount of rotation about the axis of rotation. The chain rule shows that the total time derivative of a vector observed outside of the rotating frame is the total time derivative of a particle observed in that rotating frame, and this is the contribution coming from the rotation of the axis. We just have seen that the first order derivative of angle is n cross x, and second order derivative of this angle is n cross x. Okay, substituting this one to be the velocity at the rotating frame, and this is the amount of velocity generated by the rotation. So by chain rule, this one is n hat cross x, and this one is theta dot. Combining these two pieces, we have velocity of a particle can be expressed in terms of the velocity of a particle measured at the rotating frame, and the additional velocity generated by the axis, the rotation of the axis. Double time derivative can be achieved by repeating this operation twice. That is a partial time derivative. That means the velocity, finding out the change in the rotating frame vector and the change due to the rotation itself. And if I double this operation, we have second time derivative. If I take the time derivative of this vector, front vector, we have double time derivative, and then single angular partial derivative, and then it can pass this one. Then we have a double derivative, mixed double derivative of time and angle. Here, this one also gives 1, so we have a factor of 2 in the mixed term. And when it means this one has a double angular velocity, it's the square, and the double angle partial derivative. Alright, as a result, the previous calculation shows the first order derivative is n hat cross x when theta equals 0. And this one, 2 theta dot n hat cross x dot. Because single derivative brings this, and then take the time derivative, so n hat is fixed, so only x can vary, so n hat cross x dot appears. The next one, that theta dot squared, and double angle derivative is n hat cross x. Wait a second. Alright. If I substitute double time derivative of angle by the angular acceleration, single time derivative of angle to be the velocity, angular velocity, combining with the x unit vector of axis of rotation, and the theta dot square will be distributed over there and there, so omega cross x appears. So this is the acceleration, but everything summed over, then that is the acceleration in any inertial reference frame, and this is the acceleration observed at the rotating frame. This is the acceleration due to the acceleration of the angle. This is the acceleration due to the motion and the rotation of the angle as the axis. And this is actually the centripetal force, and this centripetal force will be, this is measured at the rotating frame, so inertial reference frame is total, so it will be migrated to the left hand side to find out the measurement at the rotating frame. So at the rotating frame, this one becomes a minus value. So minus of this amount is called the Coriolis force that depends on the rotating frame. This is actually the centripetal force that makes something rotate in this way. However, in the rotating frame, it is seen to be minus value of this. So that is centrifugal force. So as a result, we have an axis of rotation, and x per, that means on this plane we have some x, and perpendicular component will be along this direction, and x per will be perpendicular to the z-axis. And we have another component, z n hat cross e rho is the lever arm direction. This is x per direction. The cross product with this e rho will be this one. All right. Therefore, in summary, in an inertial reference frame, we measure, this is capital X is the reference point at which the fixed axis of rotation is placed. This is O plus, right? O plus. From this point, particle's position is measured at the rotating frame. The velocity of a particle in an inertial frame is the velocity of that reference point, and velocity measured at the rotating frame. However, actually the frame itself is rotating, so outside the rotating frame, the effect of rotating frame will be included as omega cross xr. And the corresponding acceleration in the inertial reference frame is the acceleration of the origin and acceleration at the rotating frame, and additional components that appears due to the rotation of the axis. All right. So if I move everything to the left hand side except for the measured values at the rotating frame, we have inertial frame value subtracted by the origin's motion and additional contribution coming from the rotation. We will see that this contribution will be due to the angular acceleration, and this contribution will be due to the Coriolis force. This contribution is the centrifugal force. In a cylindrical coordinate system, So if a system is rotating about a single axis, the best frame of reference will be best choice of the coordinate system is the cylindrical coordinate system. In a cylindrical coordinate system, E1 and E2, these are fixed coordinates, and this E1 rotating and E2 rotating can be chosen as in the cylindrical coordinate system, the direction of the rho and direction of phi. However, actually this angle is varying as time goes on. This axis will keep rotating. Therefore, we have a time dependence of the unit vector along the rho and phi. This phi r stands for the azimuthal angle relative to this rotating frame. And this phi is actually the omega t. That is due to the rotation of the axis. Let us find the relation between the rotating frame basis and the fixed coordinate basis. Fixed coordinate basis are E1 hat and E2 hat. Rotating frame basis are rho hat and phi hat. And rho hat and phi hat are here. This guy is a linear combination of these components, cosine plus sine. And this one has this direction. X component is a negative sine minus sine phi. Y component is parenthesis cosine phi. Therefore, if I combine these two contributions, we have the rotating frame axis basis vectors can be expressed as a linear combination of the fixed axis basis vectors. As you can see, the sign is opposite in comparison with the normal rotation vector, because that rotation matrix is for the components x1 and x2, and in here these are for the basis. The rotation matrix for the components and rotation matrix for the basis vectors, they are opposite. So they have relationship of the inverse relation. As a result, as time goes on, this angle phi, relative angle between the fixed coordinate system and rotating coordinate system, is phi. But if we consider the case, the axis of rotation keep rotating with the constant angular velocity, then we can replace this phi with omega t, and this time dependent factor appears. Thus, if we consider expressed in terms of the fixed coordinate system, is cosine, sine minus sine, this opposite matrix, and then it is replaced with the angle of rotated angle, this omega t, and the azimuthal angle of the particle measured relative to the rotating frame. Alright, and this one disappears if we describe in terms of relative coordinates in that rotating frame. Next, what about the time derivative of this? Time derivative, because this one contains the time dependence, we can take the time derivative to find out non-vanishing values. Cosine becomes minus sine, Sine becomes cosine, minus sine becomes minus cosine, cosine becomes minus sine. And this one can be obtained by multiplying this anti-symmetric matrix, traceless anti-symmetric matrix, to the original value for the matrix. And this is actually this value. So time derivative shows that rho has a contribution of phi direction. Phi has the contribution of rho direction with negative sign. We already know that if I rotate in this the variation will give this tangential direction. So tangential direction to the left of the planar radial direction is the angle phi, and then tangential direction, this is rho direction, tangential direction of the phi is minus rho direction, right? So this minus sign appears, and that can be summarized as in this form. The time derivative of rotation axis is just omega cross that rotation axis. Z-axis is parallel to the axis of rotation, so I can also put this one. So this is consistent with our derivation of the Rodriguez formula for finite rotation. Let us next consider the fictitious force measured at the rotating frame. In a rotating frame, the actual force that can be measured in the inertial reference frame plus fictitious force. In the inertial frame, we just have derived that the velocity and acceleration measured in the inertial frame can be expressed in terms of the velocity and acceleration in the rotating frame plus the effect of rotation of the frame itself. And in here, inertial contribution appears in here, and this one is related to these two. So if I migrate these remaining pieces to the left hand side, so negative value of these will be related to the fictitious force. So if I move this one to the left hand side, becomes, this is the reference point, the origin of the rotating frame that has the dependence. If the origin of the rotating frame moves, that velocity should be included, and the velocity due to the axis of rotation appears in here in negative sign, and we have -2 and this is minus. Alright, so as far as acceleration is concerned, this is Coriolis acceleration, this is a centrifugal acceleration. Alright, and this is Coriolis force, centrifugal force. Let us look at the centrifugal force. Centrifugal force is m times omega cross minus value of m times omega cross this one. Centrifugal force is minus m omega cross r. If we apply the back cap rule, B AC minus C AB, and if I consider the negative sign, we have x omega square minus omega dot x. So omega square, the magnitude of the omega square will be pulled out, and we have xr subtracted by, so magnitude is pulled out, then you have direction n hat. This is n hat and n hat dot scalar product survives. So we have a plane. On this plane we have x, right? This x vector has the radial components, and that direction is a rho. So magnitude of the perpendicular component of x relative to the axis of rotation will be x per. So this vector is x per vector, and the unit vector of x per will be e rho hat, right? Therefore x per is the rho. X per has the magnitude rho because it is measured in the rotating frame. We put a subscript r, rho r. So this is m rho r omega squared, and direction is a planar radial direction. Okay. The centrifugal force is toward outside. Centrifugal is toward outside of planar radial direction. According to the Coriolis force, we have two mass omega times the velocity measured at the rotating frame. Minus 2m omega, so magnitude is pulled out, z-axis, cross product, velocity in the rotating frame, that is radial velocity and tangential velocity. Radial velocity on a planar radial direction is rho dot, and tangential velocity on a planar two-dimensional polar coordinate will be rho phi dot. If we take the cross product, g cross rho equals phi, g cross phi equals minus rho. So insert this negative sign inside, 2m omega, rho phi dot, rho direction, and minus rho dot, phi direction. So this is the Coriolis force. If the omega is small enough, because this is linear, and the centrifugal force is omega squared, proportional to omega squared. So when omega is small, Coriolis force dominates. Okay, in the remaining time, we consider the general property of rotation, and this is very important to study quantum mechanics. Although we are studying classical mechanics, the properties of classical mechanics is completely copied to the quantum mechanics, except that we introduced a simple principle that has the values are quantized, and two values of the coordinate and its conjugate momentum, those are not determined completely simultaneously. That is the introduction of the commutation relation of two operators representing mechanical variables. The fundamental commutation relation for the quantum mechanics involves the commutation relation for the coordinate and its corresponding conjugate momentum. However, that relation, for example, commutator of x and p is IH bar, is exact carbon copy of the Poisson bracket, except that we multiply IH bar. So the remaining piece of this class and the next class, we will closely look at the rotational property, and the rotation property will be extended in the next class for the general transformation rule for the translation and rotation and time evolution. And that one will be extended to the construction of a quantum mechanical theory. So, first, let us consider the rotation matrix for finite rotation about a fixed axis, basically. So, look at these three matrices extended from the two-dimensional rotation. Okay. So this is the rotation matrix for the xy plane. We remember cosine, sine, minus sine, cosine for the two-dimensional vector on xy plane. The same is true if we consider a yz plane and zx plane. Therefore, the rotation about the z-axis can be expressed about phi, finite angle phi, that can be copied and replaced. We replace the theta with phi, and the rotation about the z-axis does not change the value of z component. There's a unity appears in the diagonal element of the third 3 element. That is true for the 1 element for the rotation about the x-axis, 2 element for the rotation about the z-axis. This and this, we have about rotation axis is z-axis. We have xy is of the cyclic form. We have the same shape. What about the rotation axis is along the z-axis, x-axis? Then x, y, z. They are cyclic. X, y, z or y, z, x. Both of them are cyclic. So x, y, z cyclic. So the shape of this rotation matrix will be the same. But we should be careful with this case. And if the axis of rotation is y-axis, y, z, x will be the cyclic form. Y, z, x. Z, x. Then we have the same shape. However, y appears here. That doesn't change at all. But if I remove this, so we have 2 by 2 matrix for XZ. So XZ matrix should be flipped. So XZ matrix is not cyclic. It is we have permutation effect of negative sign appears. Therefore, this in this case, the matrix has negative sign on this element. Next, we consider the group. Actually, the rotation matrix form a group. The set of rotation matrix, as far as a single direction is concerned, for example, we keep rotating about the x-axis and keep rotating about the y-axis, keep rotating about the z-axis, then everything forms a group. So they commute, and the product is also element of the group. Inverse exists for every rotation, and invariant transformation, that means do not rotate. Identity is an element, and product of serial rotation is another rotation of the same kind. So that's the property of the group. But the problem is that if the axis of rotation changes, that is the non-trivial problem. However, actually that is also they also make a group. We'll see. First, let us look at the generator. This is a finite rotation about the z-axis by a finite angle phi. Any rotation about the finite angle can be sliced into n pieces, n equal pieces. So 1/n of this angle by n times. And this is true even in the limit as n goes to infinity. As n goes to infinity, this matrix, this infinitesimal rotation matrix, can be expanded in a very simple form. So if this angle is small, cosine phi over n minus sine phi over n, sine phi over n and cosine phi over n appears. Let us pull out the identity, just like what we have done when we derived the Rodriguez formula for finite rotation. So in that case, we have a cosine phi over n minus 1, sine phi over n, sine phi over n, and cosine phi over n minus 1. These two contributions survives from the order phi over n. These two contributions survives from phi over n squared. And the leading contribution is anti-symmetric, and except for these two contributions, everything is vanishing. As we remember, higher order piece, order phi over n squared or higher, does not contribute at all as n goes to infinity. And this is the by definition of the exponential matrix. We find this rotation, finite rotation, can be expressed in terms of exponential phi, this anti-symmetric matrix. As we can see, this matrix is traceless and anti-symmetric. It has only two non-vanishing components, they are anti-symmetric. If I, minus I times I equals 1, you pull out the minus I in front of the real angle parameter. This is a real, and I can be substituted in here. So this matrix, this is anti-symmetric, but more, we can say it is a Hermitian, and this is a traceless Hermitian matrix. Traceless Hermitian matrix, therefore its determinant is 1. We can extend this idea to the remaining 2 finite rotation. All right. In a similar manner, rotation about the z-axis, what we just have obtained. Rotation about the x-axis, this matrix should be the same because it is cyclic. Regarding the rotation about the y-axis, we remember the rotation matrix have to flip the sign because it was not cyclic. So G2 had opposite form. G3 and G1, they are the same form, and G2, the opposite sign. Now we say these G's, the generator of the rotation group. G1 is the generator for the rotation about the x-axis. G2 is the generator for the rotation about the y-axis. G3 is the generator for the rotation about the z-axis. Let us look at the values for explicit values for the ij element. First, consider G3ij. G3ij is minus 1 for ij equals 1, 2, plus I, minus I, plus I, for ij equals 2, 1. So Gijk equals minus I epsilon ijk. Okay? 3, 1, 2 should be epsilon 3, 1, 2 should be plus 1. So I have minus I vector. So minus I epsilon ijk will be the jk element of the generator for the rotation. All right. Then, because of this, we immediately obtain the generators of the spatial orthogonal group satisfy the following commutation relation. And this commutation relation is not for the Poisson bracket, but for just the algebraic commutator. A times B subtracted by B times A. This one shows that the rotation of mixed rotation generates a rotation about another angle. For example, 1, 2, and 2, 1. Generates 3. So you will keep rotating about the axis, y and y axis, but at the end of the day, you will find some contribution of rotated about the z-axis. So this is a special nature of rotation. So that is this one is the fundamental reason for the fundamental commutation relation for the angular momentum. So for example, Li, Lj equals IH bar epsilon ijk Lk. and that is for the orbital angular momentum, and that can also be extended to the spin angular momentum, and that can also be in general there's a general angular momentum J, that is L plus S. Okay, let us check explicitly. This is a matrix multiplication, GA, GB subtracted by GB, GA, and we need to compute the ij element for every I and j. Alright, so right here we have G A I K G B K J G B I K G A K J. Now we substitute the result. This one is a minus I epsilon A I K minus I epsilon B K J minus I epsilon B I K minus I epsilon A K J. Okay, and if I square the minus I, we have minus sign, minus I is a plus. So we have repeated Levi-Civita tensor with a single repeated indices. They are linear combination of products of canonical letters. That is, alright, that is, what's that? K A J I B delta A B I J minus sign B J B J I A minus sign B A I J, but they are the same, they cancel. So this is the final result. It can be expressed as a determinant of 2 by 2 matrix, but we can simply compare the right side of the previous formula, epsilon I A B C G C I J equals I epsilon A B C minus I is a plus A B C C I J. So C will be moved without changing the sign, CAB CIJ. Therefore AIBJ minus AJBI. Alright, these two are identical to each other. Therefore, for every component, this matrix ij element is identical to this matrix ij element. Therefore, we have proved the fundamental commutation relation for rotation. So fundamental commutation relation can be used to consider the rotation about the x-axis and y-axis. So if we expand this expression, 1 minus phi g and second order and third order, and this is 1 minus I phi 2 g2 and squared contribution and third and so on. We neglect order cube contribution. If I expand this commutator, identity contribution all disappears, and up to phi square contribution, the only surviving contribution is a phi contribution, because 1 disappears, 1g g1 disappears, 1g squared, the g squared 1, they are all vanishing because of the identity. So the only non-vanishing leading contribution will be g1 g2 style. So we have minus I squared, parameter phi 1 phi 2 angles, and G1, G2 commutator. But we know that G1, G2 commutator is IG3. So G1, G2 commutator is IG3. So we have minus I epsilon 1, 2, 3 phi 1, phi 2 G3 style. Therefore, x1 x rotation, y rotation, and y rotation, x rotation. The result is z rotation. Very strange. So this is a fundamental nature of a non-abelian structure, that they are not commutative. All right. So what happens if I rotate about an arbitrary angle, about the arbitrary axis and head? So this one, the generator can be pulled out by taking the partial derivative with respect to phi. Alright, so let us consider the case of finite rotation about an arbitrary axis and head. We recall that axis, if the axis is x-axis, y-axis, and z-axis, we obtain these three generators. The square matrix of each generator will be this form. Very similar to the case of the Pauli sigma matrix. However, we do not have an element, this empty element. The reason is that if you consider Pauli sigma matrix, you rotate. So any rotation gives some combination of two axes. So anti-commutation of the two axis contribution. So xy minus yx. Except for the two axes that are on a plane, any other contribution do not contribute. Any other axis do not contribute at all to the rotation. So rotation is only for two axes. Okay? For example, we have rotation about the x-axis. We have this only two contributions. Y-axis, this one is empty. Z-axis, this one is empty. 1, 1. So identity subtracted by this G squared style, we have a single element. Alright. If we repeat the power, increase the power, even contributions are all equal to this form. Odd contributions are all equal to a single power. So exponentiation of this matrix will give the summation of power series, and we divide into the even contribution and odd contribution. Because G squared is not an identity matrix anymore, it's better to separate the contribution of identity. The leading contribution n equals 0 contribution is identity. But from then on, squared contribution, we have the empty element, missing element. Therefore, if I make use of the result, even power is gk squared, odd power equals gk, but even is only for n equals 1, 2, 3. So the 2, 4, the 0th power is identity. Substituting all the previous result in here, we find that the I phi gk is expressed in terms of this. As we substitute these explicit matrix representations, we obtain the finite rotation formula for x direction, y direction, and z direction explicitly. So next we consider the case of rotation about arbitrary axis and head. We recall G1, G2, and G3. And this one, n hat dot G, appears in here. N hat dot G means n hat is the unit vector. That means n1 squared, n2 squared, n3 squared summed. This identity, it is one, unity. So, using this, we just square the matrix. A tedious job, but multiply these two matrices, we obtain n3 squared, n2 squared, minus n1, n2, and so on. So 1 minus this square value is this just direct product of n and direct product 1 1 1 2 1 3 2 2 1 2 2 2 3 3 1 3 2 3 3, right? This direct product. And Q, if you, it is a little bit tedious job. I have computed all the ij elements 1 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3, and substitute the result. We find this power. This is the same as the original value for the single power. That relation is identical to the case of rotating about the x, y, z axis separately. So, in summary, if I combine everything in it, single power is minus I, minus n3, n2, n3, 0, 0, minus n1, anti-symmetric matrix. Squared one is of this form. Squared one is symmetric, and the single power is anti-symmetric. The Q force, everything can be obtained as all even powers, all odd powers. They have this kind of contribution. So this exponentiated operator is recombined and use the same formula that we make use of. We have this kind of expression. Finally, at the end of the day, we have the complete result for this expression. So if you rotate about the n-axis, explicit form of rotation matrix is given. And if you multiply matrix x1, x2, x3, the column vector to here, then you will find this Rodriguez formula for finite rotation. So today we have spent a lot of time to derive this Rodriguez formula of a finite rotation, and we made use of this to find out the Coriolis force and the centrifugal force, that is the special nature of non-inertial reference frame. The inertial force depends on the accelerating frame. In addition, because we would like to extend this idea of deriving the matrix for the finite rotation, we have completed a way to find out the generators of SO3, and this one will be extended in the next class for the extension of the classical mechanics to the quantum mechanics, especially for the rotation, translation, and time evolution.